Okay, so this is Math 331 problem solving. The goal of today is to, if possible, get to contour integration and Cauchy's residue theorem in one lecture, starting from scratch. And by scratch, I mean remembering all the results you've done in Calc 3. So this is an extremely dangerous assumption to make. So how many of you remember Green's theorem or Stokes' theorem, or can at least fake it for the day? Not even getting 100% on that. Okay. You have to learn how to fake. Oh, yeah, Green's theorem. Yeah. And then you're very quickly, discreetly on your phone looking up what is Green's theorem. Okay. So there's a lot of different ways to do complex analysis. A lot of it is a function of what you know. And so rather than proving a lot of the results directly, what I'm going to do is I'm going to show that for a function to be complex differentiable, it actually turns out that it has a curl and the curl is 0. And so with Green's theorem, you get this line integral is equal to a double integral of the curl. Well, if the curl is 0, the double integral is very nice. And so as long as your function is differentiable, everything is great. The problem is what happens if your function blows up at a point. What you do is you draw a little circle around it and you throw it away, and then you have this nice region in between where everything is well behaved. And you apply Green's theorem on that region and reduce the integration to integrating over small circles about the points that blow up. So this is roughly what's going on. Let's do a little bit more detail. So complex analysis. And so I is, or I am, the square root of -1. We write some number z as x plus iy. Its complex conjugate is z bar is x minus iy. So you basically just replace all the x. You leave the real parts alone and you flip the imaginaries. Notice that x is z plus z bar over 2. Boy, those z's and 2's look a lot alike. While y is equal to z minus z bar over 2i. So I can regard things as a function of x and y, or I can regard things as a function of z bar. Briefly, complex differentiable only a function of z. Now, if I give you some function f of z, I can regard this with an abusive notation as a function of x and y. I really shouldn't be putting this in as a pair here. I should really write it as x plus iy. This is a common abusive notation. And we'll often write u of xy for the real part plus iv of xy for the imaginary part. If you want to do differentiation on the line, it's boring. How many paths are there to approach a point on the line? Yeah, essentially 2. You can approach it this way. You can approach it this way. I will yet again try my cultural references from my childhood and see if there's a non-trivial intersection. Any of you remember the Karate Kid movies? No one remembers any of the Karate Kid movies? In one of the Karate Kid movies, he goes to Japan and he learns the secret of Miyagi karate. And so the secret of complex differentiation is something like this. It doesn't have to be exactly like this, but something of that general flavor. So when my kids were younger, I used to have them and all their friends in toddler 1 and preschool draw individual curves like this to give to all of my students. Now that they're older, they're not going to do that. But if you want, I can print out some of the old ones. I've saved some. For a derivative to exist, you must get the same limit when you look at the quotient along any path. Well, on the real line, any path is not that big of a deal. But in the complex plane, it means something like this must also give the same answer. And this is why being differentiable in the complex plane is so much stronger than being differentiable on the real line, because you have to work for all these paths. So for example, if I take the function, f of z equals z and g of z equals z bar, I can look at the limit as h goes to 0 of z plus h minus z over h, where over here would be the limit as h goes to 0 of z plus h bar minus z bar over h. So here I would get the limit as h goes to 0 of 1. It's not that bad of a limit to do. Here I would get the limit as h goes to 0. Well, the complex conjugate of a sum is the sum of the complex conjugates. So the z bars cancel, and I get h bar over h. If h is real, this is also 1. But if, for instance, maybe h equals I times k, with k going to 0, then what I would get here is negative I. So this would give negative I. But if h equals k, k going to 0, so k real in both cases, this would give 1. So the limit is different depending on how I approach the origin. Or I'm sorry, depending on how I approach z. If I approach down the y-axis, if I approach along the x-axis, I get a different answer. This function is not complex differentiable. I have to have the same limit along every path. Okay, so I'm not going to go through the details. It turns out what this essentially means is you don't want anything to be depending on z bar. You want things only depending on z. You want the x plus iy to be how the variables come into play. Okay? This is the Blitzkrieg introduction. All right, so limits matter. Order matters. When you teach complex analysis, at least for the first few weeks, you keep alternating between Cauchy, Riemann, Cauchy, Riemann. It's almost like an independent sequence of coin tosses. And one of my favorites is the Cauchy-Riemann equations, because then you get to mention both of them. So let's say f is complex differentiable. And the word we like to use in complex analysis is holomorphic. Because that way we can confuse the people from real analysis. So f prime exists. Now this has to be the same no matter how you approach. So what I could do is I could take the limit as h goes to 0 of f of x plus h y minus f of x over h. I could also take the limit as h goes to 0 of f of x y plus h minus f, this should be xy, over h. So really, one of them is essentially like applying d by dx. And then the other one, we've got to be a little bit careful. I think it's 1 over I. The other one is like 1 over I d by dy. And the reason it's a 1 over y is to be very careful as to what's coming down here. I shouldn't be dividing by h. What should I be dividing by? hi or ih, right? Because I'm looking at the difference between the 2 points. The points are x plus I, y plus h, minus x plus iy. That's what comes in over here. That's why this is really an ih and not just an h. So I'm really applying these two operators. And these two should be giving me the same result. So at the end of the day, when you do all the algebra, you get if f of z is u of xy plus I v of xy, and ux means du dx, uy is du dy, and so on and so on and so on, you get ux, I always forget the order they go, is vy, and uy is negative vx. These are the Cauchy-Riemann equations. One of the things I like is I know the derivative of u is related to the derivative of v, and I know the indices are opposite. I just have to remember where the minus sign is. So if you think back to derivatives of sine and cosine, I know there's a minus sign somewhere. The mnemonic I like is minus sign becomes a minus sign for the derivative. How can I figure out where the minus sign goes? Well, just do an example. Take f of z is z squared. So that's going to be x squared minus y squared plus 2xyi. This will be u of xy. This will be v of xy. If I know that there's some relationship like this, but I forget exactly where the sign is, all I have to do is take a non-trivial example. I'll leave it as an exercise to the reader as to would it have worked to just take f of z equals z. Okay? All right. Any questions on what we've done so far? Have you at least seen The Wizard of Oz? All right, so in my mind, this is the scene where Dorothy is trapped in the witch's castle where the hourglass is running out, and as soon as it is empty, she's dead. This is how I feel about today's lecture to get to the Cauchy residue theorem before we hit 950. Okay, so we have the Cauchy-Riemann equations. Why are these useful? So let's go back to Green's theorem. So Green's theorem is something like this. You have a simple closed curve. Do you use C to denote the curve? Do you do gamma? What do you guys like to do? C, okay. So basically the integral, right. The integral, and they sometimes put a circle around it to say it's a closed line integral over C of P dx plus Q dy is the double integral over the region of dq dx minus dp dy dx dy. There's a lot of ways to prove this. The best way I know to prove it is you first prove it for a rectangle. And when you prove it for a rectangle, when you're integrating p dx plus q dy, on this piece only the p dx matters, and you're going maybe from a to probably, let's see, normally this is the point AB, I think, and this would be the point CD, so this would be the point CB. So you'd be integrating from A to C. And then here, you have to remember you're going through it in a certain orientation. So now on this top, I'd be going from the point x equals D to x equals A. And so these two integrals over P mean that. Okay? Now over here, what I can be doing is, I've got a dq dx. I want to integrate this first with respect to x or first with respect to y? X. So if I integrate this with respect to x, I'm going to get just q. So integral of dq dx. So what I'm going to do is I'm going to fix a value of y. And so if I fix a value of y, x is going to run from A to B.
Isn't this over the region?
Yeah. But I have a double integral over the region. So if I'm integrating first with respect to x, I fix a value of y, and I'm integrating along a slice. So I would have x goes from A to B, and then I would have y goes from C to D dx.
X goes from A to C.
A to C, thank you. And then y would be going from B to D. And now when I integrate this q, this is going to be the integral y goes from B to D of q. I think it's going to be cy minus q of a y. I need a dy over there and a dy up here. And if you look at this, this is qcy. Y goes from B to D. That's just integrating this part over here. And then the minus qay is coming down here. So this piece is just equal to the integral of q dy. And then you just do the other work to get the p dx term. So this gives you Green's theorem for a rectangle. And then what you do is if you have a region, what you do is you chop it up. And on all the interior pieces, this side, on this curve, I get the side going up, and on this one, I get it going down. So all the interior pieces cancel. It propagates and pushes out to the boundary. And then you have to go from, all right, well, I now have something like this. I want to replace these two things with the curve like that. So I had to do some kind of like rectilinear approximation for the curve, and you show that things are fine. A little delicate analysis is needed, but this is essentially the proof of Green's theorem. Okay? So hopefully this is enough of a review of Green's theorem that the Green's theorem result is now reasonable. Okay? We all happy with Green's theorem when we can use this? Okay. So continuing to go on, and I apologize for looking at my notes, but I have thought about the fastest, most efficient way to do this, and I want to make sure I keep going in the same order. So what we have now that we have Green's theorem is we know that there are certain functions that we like to integrate. So, our function is almost like a vector valued function, p comma q. What kind of functions p comma q would we love to integrate? So if you could choose any PQ pair, what kind of pair would you choose? Yeah, you'd choose dq dx equals dp dy because then it's 0 and you can integrate 0 very nicely. All right, so there's the Cauchy-Riemann equations. All right, so now let's imagine f is holomorphic, which means differentiable, which means continuous, on a region and boundary. If you want, maybe you want it to be continuous and differentiable on a slightly larger region that includes the curve, just to be a little bit safer. So we have something like this. Here's our curve C. And I want to integrate over C f dz. And now this is where I'm hoping you brought your physics engineering hats. This is the integral over C of u plus iv dx plus I dy. And now when I expand things out, this is the integral over C, I'm going to get a u dx minus v dy plus I times the integral over C of v dx plus u dy. Okay. What do you think I should use to evaluate this integral? Yeah, Green's theorem, right? Probably the reason why we spent 5 minutes reviewing Green's theorem and quickly proving it. Right? So we would have a double integral over the region. All right, so it's dq dx, so it's going to be negative vx, derivative v with respect to x, minus dp dy, so minus u of y, dx dy, plus I, integral over the region, dq dx, so that's ux, minus dv dy, vy, dx dy. Well, what is negative vx minus ui? This is the most efficient lecture possible, so nothing is really being done that's not needed. 0. And it's 0 because of the Cauchy-Riemann equations. Negative vx equals uy. So this is just 0. And similarly, this is just 0 by the Cauchy-Riemann equations. So this equals 0 by the Cauchy-Riemann equations. So again, in a real complex analysis class, you would do this a little slower and justify, does this really mean this? Does this really mean this? This is a physics class today. My favorite moment in freshman physics was when my professor said, in a math class, you'll spend 6 weeks justifying this step. Moving on, we see, but that's why we have classes on complex analysis. So at first, this is almost looking like something that's going to be completely useless. All we get is 0. Why would we care about that? Well, here's one reason why we might care. Imagine I want to integrate something on the real line. And maybe I'll integrate from minus r to r. And what I can do is I can complete the curve. And now I have a closed curve, and I apply my results from complex analysis. And then that means the integral over the semicircle is essentially the same, or the negative of the integral over the real axis. Well, if I'm only getting 0, then that means I now have to be able to evaluate this integral over here. And if I'm having trouble integrating along a straight line, I'm probably going to have even more trouble integrating along a curve. What will typically happen is the following. The integral over the top part is going to be negligible. All right, well, that's really bad, because if the whole thing is 0 and this is negligible, then that means that's 0. But the function is not going to satisfy our conditions. Our condition is that it's differentiable everywhere. There will be some places where the function blows up. And what we'll do is, if we have a couple places where it blows up, what we'll do is we will adjust the curve. So we go up, and then we go down, we go around, we go up, around, and then down. And then the function integrates to 0 in this whole region. And it turns out that the integral over this closed curve is the same as the integral over these little circles. You hopefully saw this when you did Green's theorem, that you reduce things to points that blow up. And then all we have to understand is integrating functions that blow up on small circles about the point that blows up. So this is now motivation for why we're going to look at very specific integrals and see that everything reduces to that. It's really this Green's theorem idea. Okay. So now, integrating polynomials. If f of z is z to the n, what do you think the antiderivative is? What function has derivative z to the n? Z to the n plus 1 over... All right, we'll ignore the plus c, even though this is about complex numbers. Does everybody agree with this? Anybody a little concerned about this? I know I said we're physicists today, but you should still be a little worried about something. What could worry you? If n is not, say it, negative 1. If n is negative 1, we've divided by 0. Think back to calculus. The derivative of natural log of x is 1 over x. All the other things are nice. You know, x squared over 2, its derivative is x. X, its derivative is 1. 1, its derivative is 0. 1 over x goes to, I'm sorry. Taking derivatives, right. Right. Then the next thing, 1 over x goes to negative 1 over x squared. We're missing a power of x. X to the first power, x to the 0th power. Where's the 1 over x term? We don't have a 1 over x term. So when we're trying to take these derivatives, there is a problem with the function 1 over x. And that's going to cause a lot of issues. So what we're going to do now is, here's the origin. Here's a circle of radius r. And I want to integrate the function z to the n dz along all z that are equal to r in absolute value. So I'm going to write z in polar coordinates as r e to the I theta. So dz, well, I can write z as actually capital R because I'm on the boundary of the circle. So I can write dz as r e to the I theta times I d theta. And again, in a complex analysis class, you would justify your intuition that you can just do all these operations as you expect. The goal is to get to Cauchy's formula. Okay? So now, this is the same as the integral. Theta goes from 0 to 2 pi. Z to the n is going to be r to the n e to the I n theta. dz is r e to the I theta I d theta. So I'm going to get r to the n plus 1 integral theta goes from 0 to 2 pi e to the I n plus 1 theta d theta. And you should think of this as, the sine of n plus 1 theta plus I cosine of n plus 1 theta. Well, if I'm integrating sine and cosine over a complete cycle, what do I get? I get 0. Unless what? So I will get 0 except for one special value of n. If n is negative 1, I have the sine of 0 plus I cosine of 0. I'm going to drop the I, sorry. Oh, wait a minute, it's cosine plus I sine, sorry. Sorry about that. And so if I take n equals negative 1, I'm just integrating the function 1 from 0 to 2 pi. So I get that this is equal to, so if n equals negative 1, the r vanishes. That's wonderful. It doesn't depend on the radius of the circle. This integral is just 2 pi. So I get 2 pi I if n equals negative 1, 0 otherwise. So I'm going to write that over here because this is such an important result. So this is, and in fact, what we'll often do is we often divide by the 2 pi I. So I'll put the 2 pi I over here, and this will be 1 if n is negative 1 and 0 otherwise. So we can integrate our functions very nicely. If you think back to the fundamental theorem of calculus, as long as n is not negative 1, I have it's called a primitive, an antiderivative, an indefinite integral for my function, and I'm evaluating it at the same points. So the difference will just be 0. If n equals negative 1, I no longer have that. Okay. Is everybody comfortable that the integral of z to the n has this special value? Everybody's comfortable with this? Okay, so we'll call this a lemma. Let's say I want to integrate along a circle of radius r, the sum n goes from minus n to infinity of a sub n z to the n dz. How do you think I should evaluate the integral of the sum? What should I do? And I do have my physics hat. What is the integral of the sum? The sum of the integral. So this would just be a sum, n goes from minus n to infinity, of a of n, integral, absolute value of z, and actually I'll put a 1 over 2 pi I. 1 over 2 pi I. And this is why some people say that 2 pi should be celebrated or not pi. Because in complex analysis, it's the 2 pi that comes in. Z equals r, z to the n dz. What's the only term that survives? A n minus 1. Or a negative 1. A with n equals minus 1. So this integral is just a minus 1. So we'll extend our box down here. So we've shown that if we have a nice function like this, whose Taylor series is allowed to include negative terms, this is now called a Lorentz series, but only finitely many negative terms. And if everything converges, then this integral is just the a to the negative 1. If you want, what we could do is we could pull off the finitely many negative values, and then we would have an integral with the positive terms. And then as long as everything converges, we've now broken it into finitely many pieces. And we've reduced this integration to calculating the negative first term in the series expansion. This is what happens if the function blows up just at one point, which is the center of the integration. What if I blow up at other points? Well, the idea is I just want to reduce the calculation to the places where it blows up. forgot to add, I am teaching complex analysis next year. If you take that class, you cannot look bored as we go through several weeks, proving all of this stuff rigorously. All right, that's the only, I should have said that as a condition for giving this lecture. Okay, so now consider the following. We say F has a pole of order m at z0 if f of z equals a minus m z minus z0 to the negative m plus a negative m plus 1 z minus z0 to the negative m plus 1 plus dot 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 with a minus m not equals 0. So the pole of order m means that we have a 1 over z minus z0 to the m at that place. So for example, if I give you 1 over 1 plus z squared, where would the poles be of 1 over 1 plus z squared? So where does the denominator blow up? Z squared equals negative 1, so it's plus or minus I. So I can write this as 1 over z minus I, z plus I. So let's say I want to find what's going on at I. I can write this as 1 over z minus I, and then I love doing this game. I have 1 over z plus I. I'm going to write z plus I as z minus I plus 2I. Why do I want to do this? I want to look at the bottom around the point I. Now, z minus I should be really, really small, because if I'm near the pole at I, z should be close to I. So what I'm going to do now is I'm going to pull out a 2I from the denominator, and I'm going to get 1 over 2I, 1 over z minus I, and then I'll have 1 plus z minus I over 2I to the negative 1. Let me pull out the 2I from the bottom, and I'll get a z minus I over 2I. This is going to be really, really small if z is close to I. What can I do if this is really, really small? It'll go to 0, but it'll be negligible, but I want to find the Taylor series expansion for this function or the Lorentz series expansion for this function about the point I. What can I do now to this piece? How can I understand this piece? I agree that it's essentially going to be 1, and I don't really need to do this, but I'd like to actually see the Taylor or the Lorentz series. What result should I use to understand this piece? Geometric series. So this would just be 1 over 2I z minus I, and then from this piece, I'll do it this way. I'll get 1 plus z minus I over 2I plus, oh, I'm sorry. I've got to write this as 1 minus negative, right? Because for the geometric series, it should be a negative. So I should write this as 1 minus minus. I could actually notice that a minus is an I squared, right? And I could cancel the I down below and put an I up top. And so this could become I over 2 z minus I. So I would get 1 plus I over 2 z minus I plus I squared, which is now going to become a minus 1/4 z minus I squared, etc., etc., etc. And so when I look at the series expansion, this should be a negative over here because it's in the denominator. It's going to look like 1 over 2I z minus I to the negative 1. Then the constant term the z minus I cancels this will be a 1 over 2I plus dot, 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 dot. And there's the Taylor series expansion. So this function does have a pole of order 1 at I. And similarly, you can show it has a pole of order 1 at negative I. And we call A minus 1 the residue of f at z naught. And so in this case, the residue would be 1 over 2I. Okay? So using a geometric series in algebra, we can actually calculate these residues in a great variety of cases. Okay. Any questions? Anybody have any idea why I wanted to look at this function?
How did you get to a 1 over 2I?
Over here?
No, in the bottom.
Over here?
Yeah.
Well, I have a 1 over 2I outside. I'm just doing the multiplication.
So is the outside term to the second term?
Yeah, because look, I've got a 1 over 2I, 1 over z minus I, and then I geometrically expand this. So when I geometrically expand this, I still have to multiply by this piece. So the first thing is everything hits the 1, and that gives us 1 over 2I z minus I inverse. Then everything hits the I over 2 z minus I. So the z minus I inverse cancels. The i's would cancel. Or maybe I forgot the multiplying by the I over 2. I'm sorry, I forgot multiplying by the I over 2. And this piece should be, I think, 1/4. Yes, sorry about that. I will admit I don't really care about these pieces because we know from integration they don't matter. All that matters is the a negative 1 term. So anybody know though why I'm looking at 1 over 1 plus z squared? What function does this look like that we've seen before? Yeah, it looks like the function 1 over 1 plus x squared. And we saw, oh yeah, the antiderivative of that is arctangent, and we use that to integrate. We'll actually be able to integrate 1 over 1 plus x squared without ever knowing the word arctan. Now, we will not be able to do an integral over a finite region, but we can go from minus infinity to infinity. All right, so the idea now is if I have something like this, what I want to do, and I'll do it to a ridiculous extreme. And just so I don't have to spend all my life drawing, I'll just kill a few of the points. So now, I guess I want to go this way, sorry. So we've got to be a little bit careful. I'm actually going about the circle in the opposite direction, but that's fine. So I take all these points, and now in this region, if these are the only points where my function blows up, in this region, the function is holomorphic, it's differentiable. I can use the Cauchy formula, and the integral will be 0. So what I can do is I can say, let's call this whole curve, C. I basically have all of this part over here. In the limit, as this thickness goes to 0, these two sides will cancel. And these two sides will cancel. And so I will get the integral over the outside of f dz. Now, it's plus the integral over the inside of f dz equals 0. So the inside, I'm actually going around the circles in the opposite direction. So when we have theta going from 0 to 2 pi, we're going counterclockwise. In these circles, we're going clockwise. So this would then become, I move this over to the other side, I would have a negative sign here, and the negative side will now give me a counterclockwise orientation. And so what we get is that 1 over 2, I'm sorry?
Have you done a double negative?
Well, I'm still integrating clockwise. I don't change the orientation when I move that to the other side of the equation. But I have a negative sign because I've now moved it to the other side. And so the negative sign changes it to the opposite. And so now I'll just state the Cauchy theorem over here. The Cauchy residue theorem. If f is holomorphic inside a curve C, say for poles at z1 to zn of residues, we'll call it a minus 1 zk, then the integral over the curve of f dz is, with the 1 over 2 pi I, is just going to be the sum of a to the minus 1 of zk, k goes from 1 to n. Okay? And the proof is that if I didn't have these points at all, if it didn't blow up anywhere, the integral would just be 0. And I do the same kind of Green's theorem argument to just throw away everything but that. Does this seem like a reasonable result? All right, we've got about 6 minutes left to do 2 examples. It's going to be close. All right? And so the first example is the one that I'm erasing that I hope we can remember. Example. We want the integral from minus infinity to infinity of 1 over 1 plus x squared dx. We know how to do this using arctangent, but let's assume we forgot our inverse trig functions. This is the same as the limit as r goes to infinity of the integral from minus r to r of 1 over 1 plus x squared dx. And now what we're going to do is let's consider the following curve. Here's minus r, here's r. Where's the only places where the function, it's usually not that hard to figure out the complexification of the function. Let's replace all x's with z's, 1 over 1 plus z squared. So it's going to have 2 poles. One pole is at I, one pole is at minus I. Which is the pole that matters? It's the one at I, which fortunately is the one we calculated a moment ago. So then we have to figure out what's the integral over the top over here. Well, if we take z to have absolute value r, 1 plus z squared is essentially 1 over r squared. Right? So we know 1 over 1 plus z squared is going to be greater than or equal to 1 over r squared minus r. The worst case for us is if z squared is negative, and so the 1 cancels it a little bit. And so if I want to then calculate what's the area of this over the top, so the integral over the arc of 1 plus 1 over z squared dz, I'll just throw in absolute values basically everywhere just to be super safe, is going to be less than or equal to the length of the arc. What's the length of the arc? Pi r divided by r squared minus 1, which goes to 0. So what this is telling us is as r goes to infinity, the contribution from the top goes to 0, the contribution from the bottom goes to what we want, and the integral over this whole region is just the residue at this point. Well, since I'm not dividing by 1 over 2 pi I have to multiply by 2 pi I. So I get that this should be 2 pi I times the residue of f at the point I. This is another notation for that. Well, we just calculated the residue of f at I. It was 1 over 2i. Lo and behold, there's pi. So that's the first integral that we've been trying to do that we can now get in a non-trivial way. This is showing you the power of complex analysis. Now, where does complex analysis rock? We could have done this, right? You're not that impressed. You know, we just spent 45 minutes on this. Come on, Professor Miller. All right. Replace the 2 with a 4. Good luck finding the antiderivative of 1 over 1 plus x to the 4th. Or replace it with a 5. Well, a 5 could be troublesome, because if it's a 5, then when x equals -1, it blows up on the real line. Okay. But if you replace 2 with 4, 6, 8, 10, we don't know those antiderivatives, but we can very easily figure out where the poles are. So as a nice exercise, try to do 1 over 1 plus x to the 4th, 1 over 1 plus x to the 6th. Okay. Any questions on this? All right. So let's do one more integral. let's do the integral from minus infinity to infinity of sine of x over x dx. This becomes a little harder in terms of how you want to replace it. And then eventually we might recognize that e to the I x is cosine x plus I sine of x. So you can actually get that sine of x is e to the ix minus e to the minus ix over 2I. And so what we might want to do is we might want to integrate from minus infinity to infinity of e to the ix minus e to the minus ix over 2ix. And then replace x with z. And so now, how would we go about handling this? This becomes a bit harder. The problem is, if we now have e to the iz over z, well, the arc, the semicircle on the top, is going to have length r. We'll have a 1 over r here that's going to cancel. What about e to the iz? This is e to the ix, e to the minus y over z. Well, if I'm in the top, y is going to be positive except at the endpoints. I should be getting some decay from this. I should be okay. The problem is the e to the minus iz over z term. This is e to the ix, e to the y over z. And so now if I integrate on the top, this is going to blow up. So what you have to do is you have to split the integral up into two integrals and do this one on the top and this one on the bottom. And it gets even better than that. Because when I look at the difference here, the Taylor series expansion for the numerator, they both start with 1s which cancel, and then I have an x, so this is going to be well behaved. When I split this up, unfortunately now this blows up. So what you need to do, and we can do this on so we will do the e to the iz over z on this piece, and we'll do the e to the minus iz over z on this piece. And we take a little detour around the origin. And so because of this, I don't include the pole. Or I could go the other way, and I could go like this, and now the pole is inside. And so we would have to figure out what to do if you only go halfway around. Based on the fact that this is a blitzkrieg course, it's probably better to go like this, so that you include the whole pole, so that the pole is inside. The difficulty now is we have to figure out what is the integral over the small half circle. And in fact, the integral over the half circle is going to be non-zero. What this essentially means is you get half the contribution of the pole. Ah, I'm integrating halfway around the pole, I get half the contribution. Okay, that seems reasonable. So it's going to be something along those lines. So we can go through and do the details of this on Wednesday. But this hopefully gives you a sense of the power of complex analysis, is that we can reduce a lot of these really painful integrals to really nice calculus problems that are just Taylor series. This is the easiest type of calculus problems, because a lot of these Taylor series is just simple differentiation or geometric series or something like that. So we are no longer integrating. That's the power of this. All right, this was a huge blitzkrieg lecture.